Thanks, Steve. Thanks all the organizers of this committee for giving me the opportunity to take part in this fascinating workshop. Can you hear me well? Yeah. Good. Can you see my slides well? Yeah. Great. So, this talk will be slightly different than the other ones because I'd like to focus on something slightly more practical, I would say, while when solving various combinatorial optimization problems, we frequently have to use column generation or cutting plane methods or some decomposition schemes, and then interior point methods have something special to offer. That's what I'd like to convince you to. This is the outline of my talk. Since so much has been already said about IPMs, I will not spend much time on it, but I'd like to draw your attention to a few interesting features. And then I will pass quickly to column generation and cutting planes, and then spend some time on warm starting interior point methods. This talk will focus on the ideas, but if anybody is interested in more details or occasionally a theorem that justifies some of the developments, then I'd encourage them to have a look at the website where there is a software and several papers available from. So, what is particular about interior point methods? Here they are written for quadratic programming, is that they replace the first order optimality conditions, which require complementarity condition to be satisfied, with that one in which complementarity condition has been perturbed, and the barrier term, the force of the logarithmic barrier, here controls the perturbation. By the way, this notation, capital X times capital S, means that component-wise xj times sj should be equal to a parameter mi, the barrier term mi. Now this has very deep consequences because the simplex method or any kind of active set method needs to make this guess and has to make a commitment how this product will be forced to be zero. So either X or S has to be zero, and we know very well this will lead to basic, non-basic partition. Of course, in more general setting, we may have basic, non-basic, super basic, and so on. But this is the key thing, the need of guessing how to satisfy this condition. Interior point methods do not have to guess, as everybody in this room, I mean in your room, probably knows it very well. And they will force zero here by gradually squeezing the barrier parameter mi. The first order optimality conditions for the barrier problem give us a very nice tool to control the distance between the primal and dual objectives. That the distance between the primal and the dual is just the multiple of the parameter, of the barrier parameter. Hence, it is always possible to interrupt interior point methods with a known distance to optimality. This is very different from active set methods, in which, as long as there exists at least one variable which has negative reduced cost, you can't really well tell where the optimum is, what the optimal function value is. So this feature of interior point methods allows to solve problems to a specific accuracy and interrupt interior point methods early enough. Well, let me summarize. There are a few attractive features of interior point methods which we should take advantage of. First of all, they excel on large-scale problems. They can easily control the distance to optimality. They are completely indifferent to degeneracy, and they are able to warm start. And of course, if anybody is interested in some of the theory of it, they can follow the excellent book of the chair of the session or my survey written already a decade ago. Now, in decomposition approaches, what interior point methods can offer is that We can apply them both to solve the master problem and to solve the subproblem. When we apply them in the master problem, we would expect to avoid the zigzagging and degeneracy using interior point notions, while in the subproblem, when, for example, we solve linear subproblem, we do not always have to solve them to perfect accuracy. We can stop them earlier and deliver subgradients, which in the early stage of cutting plane method are absolutely sufficient to guarantee fast progress. So let me guide you now through primal dual column generation method. Column generation is a well-known technique which applies to situations when we have to solve a linear optimization problem that has huge number of columns. This number, capital N, may be exponential in some situations. The columns AJ here may be implicit elements of certain set, and we do not have to have them explicitly, but we need to be able to generate them. This is enough to run the column generation process. And it works by choosing a subset of columns. So n bar is a subset of n, in which we will solve the so-called restricted master problem, which is a relaxation of some sort of the true master problem. Once we find the optimal solution of the RMP, restricted master problem, we can easily generate a feasible solution for the true problem by just filling the vector lambda hat with zeros for all columns which were not in n bar. We also know the upper bound on the solution because we solved the relaxation. How can we find whether this is optimal? Well, by calling the oracle and pricing all the columns that were not included in n bar. The oracle will check the feasibility of the current dual solution by evaluating these reduced costs. This may be done implicitly. Usually it is done implicitly. But as long as the minimum of these reduced costs is negative, we will have to add new columns to the restricted master problem. So that's the notion of the oracle. And here is the primal dual column generation method. That is the column generation method which relies on interior point solver to find the solution of restricted master problem. It's a standard column generation except those two lines which are displayed in magenta color, which indicate what is the difference, what are we going to do differently from the standard column generation. First of all, we have lower and upper bound, we have the duality gap, current measure of the distance to optimality. We'd like this gap to eventually drop below a prescribed tolerance delta. If it is not yet there, then instead of going for the optimal solution of RMP, we will find some well-centered epsilon optimal solution. And already from this point, we can, we can update the upper bound, and from this point U tilde, call the oracle and verify whether there exist reduced costs which are negative. If there are if there are columns which have negative reduced costs, they will have to be appended to the restricted master problem. However, we will also play with the accuracy with which the restricted master problems, to which the restricted master problems are solved. And instead of going always for optimality, we will ask for just small reduction of the duality gap. So it will be reduced by some number d, where this number d is greater than 1. The process continues up until there are no negative reduced costs, in which case we may say that the restricted master problem contains all crucial columns. Nothing has been omitted. I mean, those who have been omitted are irrelevant anyway, and the process stops. Such algorithm can be demonstrated to converge. However, it's very difficult to get any kind of complexity result for it. So it's just a convergence in a finite number of steps to a feasible solution, lambda, which is only delta, relatively only delta far away from the optimality. This has been addressed in the paper in Enjoy. I already mentioned that this interior point method will look for central solutions, and that's an important thing which somehow responds to the need that people using various cutting plane methods or column generation methods faced for decades. There have been known effects of instability in the column generation. Column generation and cutting plane methods jump from one corner of the polytope to another for a while and do a lot of zigzagging. Towards the end, when cutting planes are nearly linearly dependent, then they start to suffer from degeneracy. So there have been a variety of methods proposed to overcome these difficulties. There is certainly a bundle method with lots of researchers involved in it. Artificial bounds set for dual variables, so trying to create artificial box where dual variables should belong to, or level set methods. But I'd like to say that when we use interior point methods, we do not have to worry about such issues because interior point methods by their very nature follow the central path, and therefore the points which are close to the central path have these, well, Dickens ellipsoids in fact, have these trust regions to be guaranteed to be entirely contained in the feasible polytope. So it's very easy, it's very natural to obtain a very stable solution which would not go to extremities, but depending on the precision we ask for, we may stop relatively close to the optimal solution, but still remain central, that is, have this Dickens ellipsoid around the current point, which keeps the point far away from the boundaries. This avoids the degeneracy issues completely because there is no trouble of finding exact solution, which inevitably would lead to linear algebra difficulties. And it also delivers a stable dual solution. It's based really on this deep property of interior point method, which follows the central path and all the time takes into account the distances to every constraint, whether this constraint is supposed to be active at optimality or is not. The distance to the constraint is present through the logarithmic barrier term always. It's somehow the point aggregates information about the polytope, interior point. The knee center aggregates the information. Here's the definition of the Dickens ellipsoid, which defines an ellipsoid fully contained in the visible region. Of course, the ellipsoid decreases when the barrier term goes to 0, which is also pictured here in this figure. If we use this scheme, that is, we use interior point methods to solve restricted master problems, we see an immediate advantage. Here's a particular problem, the vehicle routing problem with time windows from Solomon collection, which is solved by the standard column generation, which used Cplex and went to optimality when solving every restricted master problem. And the dotted line indicates the behavior of interior point method. What we measure in this picture is the jumps of the dual variables, the norm of dual variables between iterations of restricted master problem. And as you can see, with the standard column generation, there are many more iterations required, 70 something, 71. With interior point, just 17 iterations were needed to generate all the necessary information and find the optimal solution. But also the changes of dual variables were much better controlled. They behaved much more smoothly. There were no these long period of jumps. This methodology has been used already to solve a variety of problems originating from combinatorial optimization, like uncapacitated facility location to multi-commodity network flows, cutting stock problem, capacitated lot sizing problem with setup times, or earlier mentioned vehicle routing problems with time windows. But it also has been used in multiple kernel learning and machine learning, and to solve some two-stage stochastic problems. Recently, we also applied them in very different settings. One was the truss design, so these are the very difficult engineering problems. And here we solved both the typical column generation, which involves linear programs, but also the same scheme was used in semi-definite programming, in which the cuts were generated by the semi-definite oracle. So we were looking at the global stability constraints in the design of trusses. There's also a recent development on robust vehicle routing problems. But I think it's time to close the thing on column generation and move to warm starting. So I apologize, I couldn't come to the conference, but I thought I would bring you a Scottish perspective on central cuts. So here's Rod Stewart singing, first cut is the deepest, but of course he certainly means that these are the central cuts, the cuts generated by from knee centers, from the points in interior point method.
Is that actually a theorem?
Yeah, well, we need to ask him. Now, let me move to warm starting interior point methods. So that's a situation in which a sequence of similar problems have to be solved. And I already mentioned this will be the case in column generation or cutting planes. But when you think of solving such problems in the block angular LPs, like Danzig-Wolf or Vender's decomposition, and also in all combinatorial optimization or integer programming, branch and bound, branch and cut and price, and whatever you may add here as an end. Sequential quadratic programming is another application. Any sequence of similar problems, for example, when you want to compute an efficient frontier in multi-criteria optimization, think Markowitz portfolio optimization, then warm starting becomes an essential need. So there was a brave man, John Mitchell, who was the first to attack the problem already in '88 and his PhD thesis. But since then, there have been some developments, some improvements in this area, notably those two developments, analytic center cutting plane method and primal dual column generation method. Then, in the years 2000 plus, there were lots of researchers who looked at finding some practical methodology to do warm starting in interior point methods. Why do I put this slide? Because frequently, when I go to conferences on combinatorial optimization or integer programming, the people start their talk by saying interior point methods cannot warm start. It always slightly increases my pressure, because I'd like to say that's not quite the right thing to say. They can warm start, however, they do face difficulties and they offer different advantages when applied in this context. Well, first of all, what is the difficulty of interior point method warm starts? Well, here I show you the picture in which there is one problem, this green line, the blue line defines the current polytope, and here's the central path, and here's the good neighborhood of the central path. That's where we would like the iterates to be before they reach the optimal solution. And then suddenly the problem is perturbed. The perturbation may consist in eliminating some variables, like in branch and bound, in adding new cuts, 500,000 of them, and cutting off this corner, or just any kind of perturbation of the data which rotated the polytope, which moved its facets and changed the vertices. After such a change, suppose we now optimize in this objective, and now the optimal corner should be this one, the optimal vertex will be this one. You immediately see in this picture that the new central path is completely different. And it also should warn you that should anybody try to start from the point which was very close to this vertex, all advantages of interior point will be lost, because interior point cannot just move from this point and switch to the new central path. What one really should do, and that's on this picture, is to backtrack. When I say backtrack, just to store a few iterates, or maybe store the whole history of iterates, and pick up the point which was close to the central path, from which it will be easy to switch to the new central path. One cannot allow themselves to be too close to optimality, because the switch will not be possible. That's a heuristic, of course, which can be summarized in the following way. Start close to the new central path, not close to the old solution. And maybe that's the point when people criticize that interior point methods cannot warm start. They cannot warm start like the simplex method from an optimal vertex to a new optimal vertex. When I say cannot, well, I do not know how to efficiently do it. But of course they can warm start if the philosophy of interior point method is properly taken into account. Let me just focus now on a situation in which a restricted, specifically arising in column generation, that is, a restricted master problem with n columns has been solved, and an oracle is called, and a large set of new columns is added to the restricted master problem. Now we deal with the new RNP, which instead of n has n plus k columns. The expectation is that all these newly added columns, why they have been added? They have been added because they have negative reduced costs. So they each promise certain improvement of the objective. And it is natural to expect that they are all likely to be non-zero at the optimal, or a large subset of them is likely to be non-zero at the optimal. So the warm starting conditions here are difficult. We have added k columns, possibly a large set of them, and we expect that something important will happen in these columns. So that's what the theory can deliver. If we consider these two restricted master problems, the subsequent restricted master problems, one of size n and the new one of size n plus k, assuming we had a good mean center in the symmetric neighborhood of the central path of the old RNP, we will be able to find a warm starting solution in the slightly widened symmetric neighborhood for the new problem, such that the duality gap, the complementarity gap as it is written here, is not significantly larger than the previous one. This is the old complementarity gap. This is the new complementarity gap. As you can see, it has grown by n plus k over n, which is a number slightly larger than 1, and the constant 6 over gamma, where gamma is the width of the symmetric neighborhood. This is the result presented in the paper in that program. Right. So if we were to summarize what happens with the warm starts face the difficulty with judging what will happen to the complementarity condition. In other words, how to define the optimal partition of a problem and the new problem. And here is my very superficial suggestion of when the simplex method is likely to be better, when IPM is likely to be better. If you have just a few indices changing optimal partition, that is changing from x equals 0 and non-zero s to the other thing, to non-zero x and 0s, if you have only a few indices changing the optimal partition, This is typically the case of branch and bound, or adding just one cut in cutting plane method. The simplex method is the likely winner. If you have many indices that have to change the partition, or for example, you add 500,000 cuts in cutting plane method, or deal with the general perturbation of the problem data, all constraints have been moved, shifted, rotated a little bit, then interior point is the very likely winner. So here's the conjecture. The more changes in the large problem, the more attractive IPM-based warm starts should be. And time is pressing, so time for conclusions. There is a new perspective that is delivered by interior point methods when applied in combinatorial optimization applications. In methodologies such as column generation or cutting plane or branch and bound and all its derivatives. And also I'd like to say warm starting works in this context. That is, it's possible normally to re-optimize the problems in something like 3-5 interior point iterations. Now, it's not as quick, 3 to 5 IPM iterations. It's still possibly quite a lot of time, but the simplex method sometimes after adding many cuts completely loses it and solves the problem practically from scratch. So this is still a significant improvement over the general number of IPM iterations you would have to use to solve the problem. And this brings me to the last slide. Thank you very much for your attention.